Didn't take all 2 hours. So Chris, you want to?
Sure. Yeah, first question I have, is the volume okay without light? Everybody can hear me? Okay, I'll continue trying to speak up. Yeah, first of all, good morning. Welcome to the session. Um, as we proceed here, my talk is heavily focused on gas turbine combined cycles. And as I'll go over in the bio briefly, that's really been my life since the literally 1980s. I'm not sure how many of you had that kind of background. If at some point you want me to slow down, talk about combined cycles, because I know this is more the carbon capture side, I'd be happy to do that. I'd be happy to answer any questions. So let me just start off with a little bit of my background, which means, okay. All right. Yes, so I spent most of my career with GE. 20 of those years were with GE Power. I said I was heavily involved in gas turbine combined cycles. I spent 10 years at the research center, and part of the time I managed fluid mechanics, and about 7 years I managed the combustion laboratory. So that's my background. I began my career as a nuclear engineer, went through nuclear power ops as a civilian, for those of you who are familiar with that program. Did a PhD in RPI in heat transfer and multi-phase flow. But it turned out that was a great way to get involved in combustion. With gas turbines, my first real role was gas turbine combustors for F-class. For those of you who may not be familiar, we typically talk about industrial gas turbines as in terms of class. So A class, B class, they were designed in the 50s and 60s. 70s was E class into the 80s. In the 90s, GE and the other OEMs introduced F class. F class, I'm going to talk here in F. Final temperatures were about 2300. Now more like 2400, 2450. They truly are high temperature gas turbines. Smallest F class for GE is about 70 megawatts. That was introduced as a 6FA. The largest F class is now about 260 megawatts. That's a 9FA. The OEMs in the 2000s began to introduce H class and J class. H and J class pushed firing temperatures by a couple hundred degrees. And just as a ballpark number, the H's and J's took combined cycle net efficiency over 60%. And now the best of the H's and the J's are 64 and pushing up on 65%. My last role with GE, I was honored to be product manager for the 9HA 902 gas turbine. And in a single shaft configuration, a gas turbine and steam turbine produces almost 800 megawatts. So this is no small piece of equipment. In the 6 years I was there, we sold about a dozen, and we commissioned mega projects in 6 different countries on 2 different continents. And that was a great learning opportunity. I wanted to spend some time on that background because there's going to be a theme here. Natural gas combined cycles are economically wonderful. They're highly efficient, they're clean, the air emissions are single digit. A couple ppm NOx, a couple ppm CO. However, they need to be decarbonized. There are 2 fundamental approaches to decarbonizing combined cycles. One approach is upstream, the fuel side. There's a lot of excitement about use of hydrogen, use of ammonia, use of sustainable fuels, biofuels. And I'm enthusiastic about every one of those 3 areas. I would not try to predict if they will be the winners by 2050, the market and the technology will answer those questions. I happen to be focused on the other approach, and that's the downstream approach of carbon capture. Over the last roughly 3 decades, there's been tremendous work, both by industry and by government, DOE, on carbon capture. But one of my themes will be the importance to think about how we would do carbon capture on a natural gas-fired combined cycle. Roughly 40% of the nation's power is produced by combined cycles. Grid operators love having gas and steam turbines on the grid. They're firm, they're dispatchable, they provide inertia, they're reliable. So there's a strong interest by the grid operators to keep combined cycles online. But we've got to decarbonize. And so my discussion will be, how do we decarbonize combined cycles? And there's a special challenge we have to think about. Most of the previous work on carbon capture has been focused on coal or gas plants that operate at essentially steady loads. Baseload service is wonderful. Everybody wins. The ratepayers win because it's inexpensive. The OEMs win. The plant owner-operators win. But the reality is every plant can't be in baseload. So that's going to be the theme of my discussion here. Really 3 topics. I want to give you a quick introduction to DOE and RPE, who we are. Essentially, we are the DARPA of the Department of Energy. Our role is to find and fund early stage, low TRL, typically TRL 2 to 4 technologies that are high risk, but also high reward. And our typical award is maybe starts at 500,000 to 1.5 billion in a phase 1. If they do well, there's opportunity for phase 2, which could be, say, $3 to $7 million. A big part of what we do is focus on tech to market. So you saw T2M. I had an earlier question before I talked. What does T2M stand for? T2M stands for technology to market. Our motto in RPE is, if it works, will it matter? So we work very hard to try to make sure that our technology, first of all, is successfully developed, but then is commercialized. So here we are. We started in 2007, and our first funded program was 2009. In 2023, we have made over 1,500 awards and over 74 programs. And most of our funding is awarded by program. So a program is roughly 12 to 16 projects. So a program can be roughly $40 million. Examples of programs, one is Flex, which I'll talk about. And Flex is flexible combined cycles with carbon capture and sequestration. I'm going to give you another example that I've had the privilege of working on, Gophers. Turns out underground power distribution is significantly more reliable and more resilient than overhead. It also doesn't bring risks of things like wildfire or susceptibility to tropical storms and hurricanes. But underground distribution is anywhere from 2 to 10 times more expensive. And so last year we kicked off Gophers. And the goal of Gophers is to try to develop advanced technologies that reduce the cost by at least a factor of 2, ideally more, of undergrounding. And there's 3 key elements of Gophers. So one is mapping and sensing. One of the biggest challenges of underground power distribution is knowing what's there. One of our industry experts, when we introduced the program, he said, well, what I really want you to do is develop a backhoe that won't break a gas line. And so that's the mapping and sensing part, which is knowing what's there. It could be man-made, it could be natural. If you're about to hit granite, Sure, we can drill through granite, but you want the right equipment for it. Another is another branch of the program is essentially drilling technologies. Oh, that's mine. This is essentially robotics. So use of robotic technologies to drill. And then a third, one of the big issues with underground distribution is that if you get it wrong, it's very expensive to repair. So quality of splicing becomes a big deal. If you go to the effort of undergrounding, you don't want to have to dig it all up again. So we have an initiative towards improving splicing. So that's an introduction to RPE. We originally started off with these top 3 objectives: reduce imports, improve efficiency, reduce emissions. We were later asked to improve radioactive waste management. We have multiple programs that look at essentially the nuclear fuel cycle, and also to improve energy infrastructure resilience, and that is the grid primarily, and this was the motivation for Gophers. We keep metrics of ourselves. I don't want to go through all the numbers, but just a ballpark. 150 companies have been formed by RP projects, something we're very proud of. 27 exits, almost $22 billion of value. Licenses, patents. We do track journals, but it's not our major focus. We would much rather have 2 extra companies, and if we had to have the journal articles. It's important. It's a measure of technical accomplishment, but we're really focused on commercializing technologies. Flex, okay. I mentioned the number, 40%. Well, in 2022 it was 39%. Rounded up, and that's 40. Combined cycles, I could argue, are truly the backbone of the grid. We don't have nearly enough storage yet to take advantage of renewable. My former company has a wind business. They have a photovoltaic business. Before I retired, I was certainly very proud of both. The progress of both the wind and the photovoltaic industries over the last 20 years has been incredible. What they've done for reliability, for taking costs out. Now a significant amount of the power that we use is generated through wind or solar. There's a significant focus on storage. Batteries are probably getting the most attention, and we fully support. RPE, DOE have significant battery programs. There's great progress on the industrial side, but it's just not moving fast enough. We don't have the storage capacity to truly take advantage of all the renewable generation. So combined cycles are still important. Here's kind of where we start on Flex. We need to decarbonize. And let's say you take the approach of downstream carbon capture. One of the realities, and this is where I'm going to go back to my origins. I talked about the early gas turbines. Early gas turbines were almost all peakers. And even the first F-class machine, the first 7F gas turbine, was designed as a peaker. And it's hard to believe. So it's a 150 megawatt gas turbine. In a combined cycle, it was about 57% efficient. And it was developed in the 80s. Now we look back and we say, why would you have ever developed a peaker? And believe it or not, and there's probably a few of you, I see a little bit of gray hair, almost as gray as mine. Believe it or not, in the 80s, there was a belief that natural gas was just so valuable and so scarce that we were robbing our future generations by using natural gas for large-scale power generation. Obviously, since that time, there have been significant natural gas recoveries. I don't think any of us are worried about running out of natural gas. Once gas became plentiful and inexpensive, all of a sudden our combined cycles went to that wonderful base load service that we all loved. But the world has changed. So my former company, we started seeing it probably in the early 2000s. All of a sudden we see that our plants are maneuvering throughout the course of the day. And it was partially because of renewables. Even more than it was demand driven. So our combined cycles were used, they would sit at min load when demand was low. But as demand would pick up, and one great example was tea time in the United Kingdom, our plants were always at base load for tea time. And so that's when we began to see some of the transient service. That trend has continued more and more. I'm sure you're all familiar with the duck curve. My product was 50 hertz. The first time I saw a duck curve was in California, but I think in just about every country we did business, they had their own version of the duck curve. So it became apparent to us that our gas turbines were going to operate in an intermediate mode, that base load service was truly becoming a thing of the past. Two of our power plants are here in Texas. And because I was part of it, and these are H-class, and because I was part of that team, we would watch the power plant's service on roughly an hourly basis. And it was fun because we got to a point where we could estimate the wind speeds in West Texas based on the output of our combined cycles. If the wind was blowing strong and we had significant wind generation, then our plants were at min turn down. But if there was no wind, our plants were at base load, pumping out every electron they could. So if you accept the premise that combined cycles might see some base load service, some will see it, but a lot of them see this intermediate service. And now you say, I have to couple carbon capture and sequestration. Now all of a sudden you raise a whole new set of questions. The current program director, Jack Lennard, and I came in this project just before phase 2. And at that point, we had a whole series of essentially startup carbon capture companies. And their expertise was primarily chemical process engineering. And most chemical process is a steady state operation. It's literally, it can be lucrative. So what you want to do is set yourself at a high throughput, steady condition, and then maintain that condition as long as you can to maximize your revenue. So the chemical process engineers, their background was big, complex chemical systems. And looking at these carbon capture systems, yeah, that's what we saw. These were essentially big chemical process complexes. And we started asking simple questions like, how long would it take to start this up? Oh, day and a half. What do you think what would your load rate of change be? Oh, well, we don't think we should change load. And then we push and we'd say, well, could you do 1% per minute, 2%, 3%, 5%? And in general, well, we could do maybe a couple of percent per minute, but we really don't want to. So the first major change we made was to try to focus our project teams on transient operation of their chemical systems. And they're working on it. It's a completely new direction for them. At the same time, we said, okay, well, if we need to capture carbon and essentially mimic the transient capability of a gas-fired combined cycle. Not only does the chemical process system have to have transient capability, we started reaching out to the pipeline companies. And obviously, the industry has been using CO2 for EOR for decades. It is well-established technology. But as we were reaching out, our first question was, well, let me show you the load profile of a typical dynamic service combined cycle. And so here's min load, 30% roughly. Max load, 100%. Here's daily operation. Here's the ups and downs. Here's your morning peak. Here's a couple of afternoon peaks. Here's evening peak. And we asked the question, will your CO2 storage and pipeline system respond? And the answer was absolutely not. Then one of the questions was, well, how long would it take your compressor train to start up? And we got that same answer. Yeah, roughly a day and a half. So, okay, the chemical process center, the downstream, the short-term storage, the piping, the transport, the sequestration, time constant of roughly a day and a half. We need a time constant that's in the minutes. So we're focusing this program now on developing truly dynamic carbon capture systems. Is this how the first carbon capture systems will operate? No. I think we're going to see a generation, just like we saw for combined cycles. We will see a generation of gas-fired combined cycles with carbon capture, or maybe upstream fuel processing, sustainable fuels. Sustainable fuels plus carbon capture, depending on the fuel, if it contains carbon, production carbon negative. That would be great. So I do think we're going to see a period of time where carbon capture systems on combined cycles see, at a minimum, steady service, even better base load service, because there will be some opportunity. But it's not going to be industry-wide. It's not going to last forever. So this is our dilemma. I've made comments on this already. Grid operators love the NGCCs for the reasons that you see here. We're focused on responsiveness. We're also focused, and this was a new twist that we provided. When we originally came in, the focus was truly greenfield. But keep in mind, there are literally thousands of combined cycles around the world, and every one of them is a retrofit opportunity. And many of these retrofit opportunities are plants that are essentially paid for. So this is wonderful. CapEx has paid off. However, they're seeing their operating hours diminish. They're looking for ways to increase the capacity factors. And one opportunity is to add carbon capture, assuming that you've got, and this is globally, assuming you've got the right governmental rules and regulations to properly reward carbon capture. And I'm not even going to try to cover that topic. I took a few minutes to put a page together, and this just shows some of the characteristics of this H and J class of gas turbine. So first of all, how big are these gas turbines? These gas turbines weigh ballpark 500 to 600 tons. So these are literally the world's largest gas turbines. A 1x1, it's a term that we use, which would be one gas turbine, one steam turbine. And the 50 hertz, I said, can produce 800 megawatts. 800 megawatts from one gas turbine and one steam turbine. Often you'll see plants in a 2x1 configuration. Those two plants in Texas are both 2x1s. A 2x1, 50 hertz, 9HA can produce 1.6 gigawatts. We've put together a 3x1 that's operating commercially in Malaysia, and that plant produces 2.4 gigawatts of electricity. So these are large, they're very efficient, they're very reliable. They only need to be shut down for maintenance about once a year. That's for a weekend borescope. Every 3 years, you do what's called a hot gas path. Every 6, you do a major inspection. So the availabilities are high, reliabilities are high. Here's your ramp rates. I know I have good friends at Mitsubishi. They're working to double this number. So let's say that's going to be almost 20. This is ramp rate, percent of gas turbine base load. Siemens, I run that up to 20, and I'm going to round up GE also to 20. These numbers that you see here are for 60 hertz. If you want, I can take you through gas turbine scaling. 50 hertz, 3,000 RPM. 60 hertz, 3,600 RPM. The key in the design is that you want your tip Mach numbers to be about Mach 1. And so if you're moving more slowly, 3,000 RPM versus 3,600, what you do is scale up your geometry. And if you scale up your geometry, you increase your airflow. If you increase your airflow, you increase your output. And that's how industry's been scaling 50 and 60 hertz gas turbines literally since the 1960s. So these are numbers for 60 hertz. So let's take the one that I'm familiar with. 640 megawatt combined cycle. Turns down to 30% with no problem. So 1/3 of 640 is 200, ballpark 200. 20% load per minute. That says that you can add 450 megawatts to the grid in 5 minutes. And that's great, and grid operators do it all the time. But that's the performance we have to see from the carbon capture system. And that's our appeal. So flex. Now, I mentioned ballpark numbers. Phase 1 RPD project, 18 months, 11.5 million spread across 12 teams. I want to mention here that in addition to the technology, we also had a modeling initiative. We had both NREL and Princeton working the economics, trying to figure out what the grid of 2050 will look like. So it's an important part. We just kicked off phase 2, 36 months, 33 million. And we want to culminate with some fairly large pilot projects. And I just want to touch briefly, these are the technology teams, Georgia Tech, RTI, Luna, Envergex, 8 Rivers. And then we've down selected to Princeton only for the modeling. And I touched on a few of these points, but these were somewhat new realizations as we brought the combined cycle expertise into the carbon capture discussions. I think we were surprised that some of these topics had been investigated more heavily, but obviously the focus had been more on plants that operated on a steady state basis. So a couple of things though had changed. One that was very important to all the OEMs. If things go well, you want a 30 to 36 months NTP is notice to proceed. That means such a contractor signed and down payment is provided. 30 to 36 months NTP to COD. And then this is the industry expectation. This is what the performers are based on. This is what you got to do. So the message here to our CCS teams is, I know chemical process plants can take 6 years to build. The industry expectation is 30 to 36 months. That's what you got to be prepared for. Maintenance intervals. I gave you numbers earlier. The carbon capture and sequestration, it has to follow the same maintenance. I don't know a power plant operator in the world who would say, yep, I'm ready to accept lower availability to decarbonize. The expectation is they've got to the same numbers. This is kind of my pet peeve coming out of the industry. One of my jobs as a research, I was part of a team that would look at all the interesting ideas that we received for power cycles. And it was just amazing the incredibly creative ideas we would see written in lines and boxes. And, you know, everybody loves doing heat balances. It really is fun. But it's just so easy to draw a line from one box to another and just assume everything's going to work and there won't be any losses. There won't be any heat loss. There won't be any pressure loss. So we're seeing just lines all over the place. We saw lines. Our gas turbine. You try to do a compressor extraction on an H or a J class gas turbine. You know how long the OEM is even going to talk to you. They have zero interest. Combined cycle steam turbines, in general, unless they're specifically designed, they don't have extraction points. Some of the chemical process, they just seem to assume that we could provide steam at any time, at any point, and it was not going to impact the rest of the system. Back pressure on the gas turbine. These carbon capture systems, yeah, they have pressure drop. Some of them had a lot of pressure drop. What happens if you back pressure a gas turbine? You have to redo the aeromechanics at a minimum. I guarantee you lose performance. But you now in a new aeromechanics space, you need to go through and do things like wind box testing, you have to do ping testing, you've got to do all the analysis to make sure you're not going to have an issue. SCRs, we're trying to raise this topic. SCRs take about 10 years to integrate. They're great. They have no moving parts. They'll take a 25 ppm NOx gas turbine and drop it by 90% to 2.5. They're robust, they're reliable, we know how to maintain them. They're typically placed about midpoint in the HRSG, which is different from the carbon capture, which are typically just upstream of the stacks. And the reason is they want nice, cool exhaust gas. They do not want 700-degree exhaust gas, which is what SCRs like to operate. One of the questions is, do you even need an SCR? So in some carbon capture systems, there will be a change in the NOx. Some will pull out NOx based on the chemistry. Some may not pull out NOx. Some may actually add NOx. So I don't want to make a statement. So it's not something we've studied, something we want to study. The NOx will be different. So think about how to integrate with the SCR. I mentioned extraction points. Something that you would see, again, with slide diagrams, is they would just say, okay, we're going to turn off the low pressure steam turbine. Well, oh, by the way, they're all in the same shaft. So turning off one section of the steam turbine is not nearly as simple as you think it is. And then if you do turn it off, all of a sudden you've got to worry about your thrust balances, your thrust bearings, make sure everything's okay. We were really surprised. Some of the carbon capture systems actually have greater footprint than the plant themselves. And then, so every combined cycle is built with maintenance access, with laydown area. The EPCs go to great pains to make sure that the maintenance topics are covered. The carbon capture systems are going to need the same type of engineering. And then CO2 purity. Most of the carbon capture systems that we saw would say, yeah, we'll give you 90% CO2 purity. We'll give you 95%. Great. What else is in there? And when we went to the pipeline companies, we said, what's your spec on CO2? They said, oh, it's 99.5. We really prefer 99.9. So there's this gap. How do you go from 90% CO2 to 99.5% CO2? And if you don't, the first thing the pipeline operators will say is, Well, we'd like to work with supercritical CO2. All right, that's a fairly large window on the phase diagram, but it's not infinite. These impurities change the phase diagram. Not sure how many of you had the benefit of studying multi-phase flow, but there's a whole field of multi-phase flow instabilities. And you hear it in your own home if you have steam heat. You hear the knocking at night, which is basically condensation instabilities, condensation shock. Well, it's one thing in your home heating system. It's another in a industrial scale supercritical CO2 system. So all of a sudden, things like condensation shocks, the strength is enough that you really have to worry about protecting your system. So the whole topic of CO2 purity has got to be addressed. And I think we were surprised with the mismatch. In fact, maybe you could just summarize at this point. One of our takeaways is that we've got to get these three communities talking to each other. The gas-fired combined cycles, the carbon capture systems, and then the downstream. But this is also where I want to summarize. The reason I gave you a little bit of that background of how we saw our combined cycle operation changing in time. We started off as peakers, we went to base load, and now most are in intermediate. Making that transition from base load to intermediate. My former company had the benefit. There was an aircraft engine company, one of the best, that had an operation in Florida. And they chose to move all their engineers from Florida to East Hartford. And about a third of them said, there's no way I'm going to move my family north. And we happened to have about 200 openings for engineers in Greenville, South Carolina. And we were able to convince them that the climate in Greenville is almost as nice and maybe even better than Florida. So we were very fortunate to bring in a couple hundred experienced engineers who'd been working on jet engines and knew everything about operational flexibility. They understood transient distress mechanisms. They were experts in things like high cycle fatigue. And they were also, one step further, they were also experts in what we termed multi-physics distress mechanisms. And when we're undergrads in engineering, we learn how to do a fatigue analysis, we learn how to do a hoop stress analysis, a buckling analysis. But it's left to the student to think about, all right, how do we address combined damage? And if you go to the ASME conferences, you'll see whole tracks on this topic. But we were very fortunate. We brought in these couple hundred engineers that knew how to deal with transient operation. And over about a 10-year period of time, we improved our gas turbines and our steam turbines so that they could achieve this highly flexible operation. So I want to emphasize, this is completely feasible. It takes time, resources, engineers. We are strongly encouraging, we're trying to fund a truly integrated dynamic modeling exercise. And it's not to include just one of these three, but it's dynamic modeling, and you could even picture it. And the pictures you have, let's start off with maybe a dozen combined cycles, and they all have carbon capture. And you've got some CO2 collection areas and some CO2 disposition areas. It's all got to be tied together. And this is completely doable. If I was 25, I'd take it on myself. So it's completely feasible. Let's enjoy maybe a 10-year period of time where we can do carbon capture on a steady basis. But let's also prepare, just learn the lesson from history, that the time will arrive when a steady state system is just not up to the job requirements. At some point, if we're going to continue to use combined cycles, if we don't go the route of upstream carbon capture, which is entirely possible, If we want to continue to rely on combined cycles, we're going to have carbon capture systems that have the transit capability, and the downstream system will also need to be able to accept CO2. Ideally, look at the natural gas system. So natural gas is a wonderful molecule. I alluded to it earlier. The phase diagram for natural gas is wonderfully simple. It's easy to compress. It's easy to move. The compressibility of the natural gas system is essentially the biggest capacitor we have for our power generation system. But we're not going to have that anymore. We're going to have a system that is just as good with CO2. I want to close just by highlighting our total budget on a yearly basis, our annual budget, is about $500 million. Our mandate is high risk, high reward. One of the things that we look forward to doing is our annual summit. This year's summit will be here at the Dallas-Fort Worth area, May 22nd, 24th. Because we address the entire spectrum of energy, transportation, storage, generation, T&D, it is a great opportunity to see the entire energy spectrum, and I would encourage you to attend if possible. Last year we had over 2,500 attendees. I think this year we're looking at over 3,000. I'm going to stop here. Thank you for your attention, and depending on time, I'd be happy to take any questions. Sure, go ahead.
Yeah, boy, great talk. Lots to think about. So do you think maybe one way to transition would be to kind of bridge the gap with gas turbines would be those facilities that work behind the meter on Bitcoin mining or something like that? And if that were the entry point that you could kind of experiment with,
Yep.
What other technologies besides like ambient capture might we be looking at?
Sure. I am qualified to answer the first. I would agree. I think Bitcoin mining, data centers, I think it's a great opportunity because it truly, I think it's going to be relatively steady state operations for a significant period of time with enough power generation required that it's going to matter. I think it just makes perfect sense. I also get to help out on some of the nuclear programs that we have, and we're very focused on nuclear fission for data centers. So I think it's a great opportunity. As far as the different type of carbon capture systems, I've been with RPE for 2 years. I've only been doing carbon capture for a period of time. I am not the best person. I would suggest my peers here could probably do a better job. I know we had Tom from Fossil yesterday. Tom Sarkis would be a great resource. He spent his entire career looking at carbon capture, and my suggestion would be to give him a chance, or his organization, a chance to answer the question.